Hi, welcome back. Today I will give an in-depth mainboard analysis about the PlayStation 4 Pro. If you are having problems with your PlayStation 4 or you just want to learn more about how the console works, then you have come to the right place. In this video I will give a detailed look at the PlayStation 4 Pro hardware. Secondly, I will give some general troubleshooting tips for common issues like the Wi-Fi problems, white light of death, the blue light of death and no power behavior. Lastly, I will provide diode measurements for the different components that are used on the mainboard. I will also provide resistance measurements and standby voltages and power on voltages that are being used at the PlayStation 4 Pro. In this video I will be analyzing the PlayStation 4 Pro model, but all this information can be applied on all PlayStation 4 models, as long as you can identify the components that are used on the mainboard and where they are located. The PlayStation 4 Pro is introduced by Sony in 2016 and it's an upgrade over the original version of the PlayStation 4. So the PlayStation 4 Pro offers better graphics and better performances. This type of video takes a lot of time to produce, so if you like my content, please give a thumbs up and subscribe to my channel to help the channel grow. So let's start. Sony released three PlayStation 4 models. The first one is the Fat model, and that was released in 2013. Then we have the Slim model and the Pro model. Fat was the original PlayStation 4. The Slim model was more compact if you compare it to the original one. The Slim model had a quieter cooling system and a reduced power consumption. PlayStation Pro was released in 2016 and it was an enhanced version of the PlayStation 4 with an improved GPU. It had double the GPU power compared to the original one and it had more CPU clock speed. So this was the more advanced version of the original PlayStation 4. And you can see here that every model had different series. And there are a lot of different mainboards and components used in PlayStation 4. So it's hard to analyze all those mainboards. And because there are a lot of different components used and different models, different mainboards, different power supplies, I cannot analyze all of those different components. The analysis that I will be doing on the NVB003 can be applied to all models, as long as you can identify the components and where it is located on the mainboard, because the architecture is still the same as all the versions. This is a troubleshooting flow diagram that I use for the PlayStation 4. This is just a generic flow diagram, so I made it myself. Here you can see the most common problems that is occurring on the PlayStation 4, also the PlayStation 5. When you press the power button, there are two conditions. You have nothing, so no sound or no light, or you have some sound and some beeping sound. If you have a no power condition, then check the SMPS power supply. Check if there is a 5V standby power present. And when you press the power button, if it can deliver the 12V. Is the power supply good? Then check the boot sequence, so check all the standby voltages that are present on the mainboard. Check the power on voltages when you push the power button, and if everything is okay in this diagram, yeah, then most probably you have a bad Southbridge IC, so you have to check the Southbridge circuit. In the other situation, you have power, it stays on, then you can check the LED color, so if it is blue or white. If it is pulsating, then you have to check all the power on voltages. If there is any voltages missing, check the hard drive, check the random access memory, check the APU, because these components will cause a blue light of death. If you don't have a pulsating blue light but a white LED, but there is no picture on the screen, then most likely the HDMI encoder IC is bad or something in the HDMI circuit. When the console turns on and then off after a beep, then you have to check all the standby voltages and also all the power on voltages. This is a mainboard of a PlayStation 4 Pro, and this is a model of type NVB003. This is the APU, so this is the central processing unit or the graphical processing unit. All calculation will be done by this processor. The power for this APU comes from these 6 power phases. I suspect that the 5 power phases here is being used for the GPU and 1 power phase for the CPU, because the main coil, so on this side there is 12V and it will provide power to these switching MOSFETs, and this output will go to the GPU side. And the last power phase has an isolated circuit. It has its own coil, so here's also 12V present, and this power rail will go to the APU. So I suspect this is the CPU power delivery. Here is some circuit to do some power stuff. It's not known exactly what it does. The 5V power on power rail is being created in this region. So this is the buck converter that will convert 12 volts to 5V power on. The 5V power on will eventually go to the USB circuit, and from there it will go to these capacitors that will provide the 5V for these two USB 3.0 ports. This is a 3V battery that is used for the real-time clock. This is a USB 3.0 hub controller. It connects the two USB ports here and the USB ports here to the Southbridge, and the Southbridge is located on the other side in this region. In this region you can find the buzzer or the speaker circuit. This is some enabling or disabling circuit, so on the other side there's 3V standby present, and the basis of these transistors will go to some chip that will control this power rail. What it exactly does, I don't know, but it is some enabling circuit because of the number of transistors here. This is the Blu-ray controller. It will control the drive, the Blu-ray drive. This is the power regulator for the 5V SATA power delivery that will go to the hard drive. The SATA hard disk will be connected here, and the power for the hard disk comes from this power regulator. Here's also some power management IC. It will create 1.9 standby voltage, and this is an SBV IC. So in this region there will be a voltage rail of 1.9 volt being created. This is a multi-phase buck controller. It will control all those drivers for every phase. This is a driver IC, and the controller will coordinate all those drivers with the correct PWM signals. Also in this region, on the other side, there's a power driver IC, and also on this power phase. And the PWM signal for every phase comes from this main multi-phase buck controller. Here is some memory. It's not a flash memory, but a DDR memory. One is located on the top side and one is located on the back side. This memory is being used to load some firmware from the Southbridge or from the NOR IC. On this side, this is the back side of the Southbridge IC, and here you can measure some voltages that is needed for the Southbridge to operate. It needs 1.8 volt, 3.3 volt and 1.1 volt. This is the standby power connector from the power supply, so 5V standby will be coming into this connector. When you turn the console on, it will send a signal back to the power supply. It will deliver or generate a 12V power on, and it will go to this connector. So when your console is turning on, it will get its 12V from this connector. This is also a power phase. I do not know where it is used for, because on Mainboard the NVB003 this power phase is missing. In this location is also some power circuit going on, of maybe some enabling circuit. I don't know exactly what it's been used for, but yeah, if you see this combination of components, it is some enabling or disabling circuit. This is the Ethernet port where you connect your UTP cable. This chip here is a UTP cable interface. It isolates the cable from the circuit. This is a USB 3.0 port. This capacitor will be delivering the plus 5V USB to this port. This is an optical audio output. This is an extension port where you can extend the functionality of a PlayStation 4. So this power phase will be generating the power supply for the RAM memory that is located on the bottom side. This power phase will also generate a voltage for the CPU or the APU. Then we have the HDMI 2.0 port, and the data lines coming from the encoder IC will go straight to the APU. So these are the main components that are used on the top side of this mainboard. This is the bottom side of the mainboard NVB003. This is the back side of the APU. And on these capacitors you can measure the 0.9 volt and the 1.0 volt. We have 8 RAM modules located on 3 sections, top, bottom and on the right. And this area is the bottom side of the HDMI circuit. This is a power stage driver IC for the RAM. This IC gets a PWM signal. PWM signal comes from this multi-phase buck controller. This PWM signal goes to this power stage for the RAM, and it will also go to the power stage driver for the CPU. So this power stage driver IC for the CPU will drive 2 MOSFETs. one high side MOSFET and one low side MOSFET. Those two MOSFETs will be switching, and this voltage is for the CPU. So this power driver IC will drive two MOSFETs, one for the high side MOSFET and one for the low side MOSFET, and this power phase will provide voltage for the random access memory. This is a USB connector, and this USB connector will provide plus 5 volt USB, and this comes from this MOSFET. So when you press your power button, 5 volt power on will be generated. It will go to this MOSFET. This MOSFET will turn on, and then it's called 5 volt USB. This is a Southbridge. This is an important component because the Southbridge connects the low speed devices to the high speed devices like the APU. So this is the chip that interacts with your power button, your buttons on your consoles, the USB signals. This component here is a 25 MHz crystal. This chip here is the NOR BIOS IC. So the firmware is stored in this chip. This rectangular component is the RTC clock of 32 kHz. This power management IC will generate different voltages that is required for the Southbridge to operate. This is the first DDR memory. So this one is on the bottom side, and on the top side there's the other one. This square metal component is the Wi-Fi and Bluetooth circuit. So these test pads are data lines that will go to the APU. By measuring the test points in diode mode, you can determine what the health is of this APU. This connector here is the data connector for the Blu-ray drive. This is also a ribbon cable that you have to connect to the Blu-ray drive, and this connector will provide the power to the Blu-ray. So this chip here will control the motor of the Blu-ray drive. This connector here is for the power button. This chip here is the Syscon IC. This connector here is for the Blu-ray eject button. These two MOSFETs are the same as this MOSFET, and these MOSFET will provide the 5 volt USB power to the USB connectors. So when you press your power button, the 5 volt power on will be created. It will go to these two MOSFET, and these two MOSFETs will be turned on, and the power will go to the USB connector. This chip here is responsible for creating the 5 volt power on. This is a power stage driver. It will drive a high side and low side MOSFET. This is the high side and low side MOSFET of the 5 volt power on buck converter. The input of this buck converter is 12 volt, and this 12 volt will be converted into 5 volt. This is the fan connector. The fan connector will provide 12 volt to the fan. It also gets a PWM signal, and most probably the PWM signal will come from the APU. So these components are all located on the bottom side of the mainboard. The first thing that I do when I get a PlayStation that has a no power behavior is to check the standby boot sequence. With the standby boot sequence, we can determine if the PlayStation 4 is initializing in standby mode. So when you provide power to the mainboard, it will initialize the Southbridge and read some data, and that action will translate in a different current draw. So in a healthy PlayStation 4, when you connect the power, let's say this is the power supply, you provide 5 volt to pin 1 and 4, and you connect the ground to the ground pin. And when you turn this power supply on, you will see that the current starts from 23 milliamps, it will jump to 125 milliamps, and in the second stage it will go back to the 30 milliamps. If you see this behavior, then you have a good working mainboard. When you don't see any current spike from the first stage to the second stage, then most probably you have a bad Southbridge. If the first stage and second stage is stuck at 99 milliamps, most probably the PlayStation 4 is not initializing, and this could mean that the Southbridge is dead. But before making that conclusion, please check the 32 kHz crystal if it oscillates, because flux under the crystal will prevent the crystal from oscillating. When the first stage and second stage is stuck at 7 milliamps, it could indicate that the Southbridge is bad, but there can also be a control signal missing, so the signal doesn't reach the Southbridge. So this standby power connector is located at area 29. This connector is located near the 12 volt connector. Also remember, this connector is different on different models of the PlayStation 4. The white light of death on a PlayStation refers to a hardware or software issue where the console displays a solid white light but fails to output any video signal or proceed to the user interface. So this issue indicates that the PlayStation is powered on and it has passed initial hardware checks but cannot complete the boot process or establish a display connection. And this problem can be caused by different causes. One of those causes can be a bad or failing hard drive. This can also cause a blue light of death or a no display, so white light of death. You have to check the drive by testing it on a PC and check the hard drive's health with a software to see if there are any bad sectors on the drive. The next one is a bad HDMI connector, so the pads here could be disconnected or the pins inside of this HDMI connector can be faulty. Next, check the HDMI filters. So these are the HDMI filters. So on point A to B, there has to be continuity. So each line has to go straight to the next point. And if there is a short here between those two pads that are crossing each other, then that is not okay. And if there is no continuity here, then you have a bad filter. Also check the diodes and capacitors near the HDMI circuit, because you can have a shorted diode or a capacitor. The most common fault is a bad HDMI encoder IC, and this one goes bad very often. And most of the time you cannot read any deviating diode measurements near this IC. So everything is measuring okay, but still this IC could be faulty. Next is to check all the components near the HDMI encoder IC. Check if the solder is not bridged between different pads, because when you remove the shield, it could bridge some components together. So please check if the soldering of all those components is okay. The most common fault on a PlayStation 4 is the blue light of death. The blue light of death on a PlayStation is a critical error where the console gets stuck in a state indicated by a pulsating blue LED. This issue prevents the PlayStation from booting up properly, leading to a non-functional system with no output or any system interface. The blue LEDs can have different behaviors. So one of those symptoms is when you turn on the console, it turns on, you get the blue LED, and after 1 second it turned off. There are many components that can cause this problem. One of those is a bad APU. So check the capacitors underneath the APU for shorts. You can have bad solder joints under the APU. So then you have to reflow or reball the APU. Also, one of the causes can be a bad power supply. So you have to check if the 12 volt is created when you press the power button. Next, if you turn the console off and you turn it back on and nothing else happens, then the power supply can be bad. So also check the power supply. Next, if you turn the console on and then the console turns itself off again, and when you try to turn the console on again, it powers up. Then you could have a bad Southbridge. You can solve this by replacing the Southbridge or a reballing or a reflowing the Southbridge. The other symptom is called 6 seconds blue light of death. So the 6 second blue light of death, it will be pulsating a blue LED for 6 seconds, or it will stay solid after 6 seconds and it will stay constant blue. Then you have to check the fan. If the fan is not spinning, then the Southbridge could be faulty. And if it starts spinning and then stops, then it's also an indication that the Southbridge could be faulty. Also check the 3.3 volt standby power rail. This could be shorted, or the Southbridge could be shorted or defect. So the 3.3 volt standby is one of those critical power rails. And the other symptom is the long pulsating blue light of death. So that blue LED will start pulsating indefinitely. And the cause can be again a shorted RAM module, a bad hard drive, a bad Southbridge, and bad HDMI circuit. There could also be some broken or missing components on the mainboard. And also when the console is overheating for a long time, this will also cause solder balls under the APU to crack, and then you have to reflow or reball the APU. A bad hard disk can also be a cause of a long pulsating blue light of death. and you can test it by removing or disconnecting the hard disk. Then the console must go in a safe mode. Also check if the USB is getting the 5V USB power. Also, you can test if the APU is a problem. Maybe there are some cracked solder joints underneath the APU. What you can do is add some pressure on top of the APU and see if the PlayStation is booting up. So if you get a PlayStation that is in the 1200 series, check the physical state of the RAM, look for burn marks or overheating symptoms. Also, if you drop the PlayStation, it can cause RAM issues or APU issues because, yeah, again, solder joints could be broken or ripped traces, and that can also cause a long pulsating blue light of death. Corrupted firmware is also a cause of a blue light of death. You can desolder the NOR chip and validate it or rebuild the software using the PlayStation 4 NOR validator software. PlayStation 4 NOR validator verifies the integrity of this NOR flash memory, and it ensures that the data stored within that chip is correct and has not been corrupted. After you check that the NOR flash is okay, then you can solder it back on the mainboard. If you get an intermittent blue light of death, so not all the time but sometimes you do get an not bootable PlayStation 4, then this can be the cause of a bad hard drive. Check also if you can go to the safe mode when you disconnect the hard drive. And you can also check the hard drive on a computer and check the health with a software called Crystal Disk Info. And yeah, corrupted flash memory can also cause blue light of death. So as you can see, the blue light of death is a hard to fix fault. So when you check everything and everything seems to be okay, the firmware is okay, there are no shorts, all voltages are present in standby and in power on mode. And yeah, the conclusion can be three things. It can be still some firmware or some software that's corrupted. Second one is bad RAM modules or DDR memory. And the third one is a bad APU. Most of the time the problem lies with a bad RAM module. In this list I will list some generic problems. The first one, no power after firmware installation, so after a firmware update. So if you go to safe mode and it works, and after installing the firmware to the console, it doesn't turn on anymore, or the button is responding slow. So when you press the power button, the console takes a few seconds before booting up. This could indicate a APU issue. So you have to reflow or reball it, and if that doesn't resolve the issue, then you have a bad APU. When you have a no power symptom, you have to test the power supply. You can connect the white connector to the 5V standby connector, press power on the console. The power on command will eventually go to the power supply and that will generate the 12V power on. When you removed a Southbridge, then you have to check if there isn't any flux underneath the 32 kHz oscillator, because if there is flux underneath, it will prevent this oscillator from running, and then the Southbridge will not work. And when you press the power button, the console doesn't react. That's because the Southbridge isn't working. If the PlayStation is stuck in a safe mode and you cannot do anything, this problem could be a faulty hard drive. When your console is overheating, the console will turn itself off and will also make some beeping sounds. When you power up the console and you hear the fan spinning at the max RPM, and then you hear a beeping sound, also with a red LED turned on, then your console is overheating. So check the thermal pads on the RAM modules and the APU, the thermal paste. When the Blu-ray drive is not accepting any disk, then check the Blu-ray circuit for missing or damaged components. When the Blu-ray drive doesn't have any power or the eject button doesn't work, check for blown fuses near the Blu-ray circuit. This is a very common issue that some fuses are blown near the Blu-ray drive. When you see this error code and your Blu-ray drive is fully functional but it doesn't work, it cannot read any data or something, then this could indicate a problem with Renesas IC, and this is an IC that you cannot replace because they are married to the board. When the PlayStation has a no power condition, and the problem was with a shorted power rail that goes to the APU, after you repair those power rails and then you get a blue light of death, then most of the time the APU is dead. Because the GPU power rail was shorted, 12V can have reached the APU, and when 12V reach the APU, it can blow the APU. You could also check if the RTC battery is above 2.8 volt. If it is empty, it can indicate a shorted Southbridge or some problem between the RTC battery and the circuit that goes to the Southbridge IC. Because if the Southbridge is shorted, it will draw all the current from the RTC battery until it's empty. And then the Southbridge chip will not work. When you have a blue light of that, most of the time the problem is in this area. So the problem could be a bad APU, the HDMI circuit, or the GDDR5 RAM modules. So if something in this circuit is not working, you get the blue light of that. Also, if the NOR IC is faulty or the firmware is corrupted, you also get the blue light of that. When only the HDMI circuit is faulty, most of the time you get the white light of that. Here you can see the diagram of the PlayStation 4 architecture. So in the middle, this is a Southbridge. The Southbridge communicates with the two DDR modules that's located on the top and the bottom of the mainboard. Southbridge also communicates with the NOR IC. So the firmware is stored in this NOR IC. The LAN module, the wireless module, so the Bluetooth and the Wi-Fi signals, goes to the Southbridge IC. All USB 3.0 ports on the front and on the back, also the extension port, all those data will go also to the Southbridge. So the hard drive is connected to a SATA bridge. From SATA bridge it also communicates with the Southbridge. This is the Syscon chip, and the Syscon chip is between the APU and the Southbridge. So the Southbridge and the APU are communicating with each other through a PCIe data lanes. So the APU communicates with its main DDR5 RAM modules. So the APU sends its graphical data to the HDMI encoder IC, and from there it will go to the HDMI port. So this HDMI port is not connected to the Southbridge IC. It will go from the APU to the HDMI encoder IC, and from there it will go to the HDMI connector. You can see that the Southbridge is the center of the most input-output operations that is done on the console, and it will communicate with the APU. So when the Southbridge is not working, most of the time you have a no power condition. So this is a global overview about the architecture of the PlayStation 4. The UTP cable interface is located in area 27, that is in this area. This is the cable interface. This is the datasheet of this cable interface. The purpose of this component is to provide magnetic coupling for Ethernet transceivers to ensure that the signal is okay and to reduce the electromagnetic interference, so the EMI. You can see here the data lines, and these data lines are isolated from the network and the device. So this is the network side, and this is the device side, so the console side. So this component offers electrical isolation between the network and the console. So this component protects the console from voltage spikes. The LEDs on the console are connected by a ribbon cable to this connector. So this is in region 40. This is the PCB board where the LEDs are located for the white light and the blue light. And this PCB board is connected by a ribbon cable from here to the connector. So these LED statuses on the PlayStation indicate the system's operational state, helping users to understand what the console is doing. So if there are any issues, you can see it by the state of these LEDs. So you can have a solid white light, blinking white light, blinking blue light or no light. Here you can find some diode measurements. So in diode measurement, the red probe is connected to ground and the black probe is connected to the pad that you are measuring. So in this case, the first pin is ground and the rest of those pins are data lines. If you see a big deviation in the values, then you know you have an issue. On this pad and on this pad you can measure the standby voltage of 4.7 volts. The power button PCB board is connected by a ribbon cable to this connector. So this is in region 38. This is region 38. So this is the connector. The first two pins and the last two pins are ground. and on the middle pin the standby voltage of 3.3 is present. From this connector the ribbon cable is connected to this PCB board, and this is the power switch. So the middle two pins will go to this power switch PCB board, so the 3.3 volt will be present here, and when you press this power button it will short this 3.3 volt to ground, and that will create a pulse. Because this line is connected to the Southbridge, the Southbridge will see this pulse and then it will start the boot sequence. So eventually the Southbridge will communicate with the NOR IC, and will also control the system's power states transition. So it will send signals to the power supply to turn it on, and also to generate some voltage rails. On the back side of the USB there is a USB 3.0 port. This is located in region 25. So this is the back side of the USB port. When you turn on your console, it will create 5V USB power on this pin. In green are the diode measurements, and as you can see each data pair has the same value. So if one of those pairs is different, then you know you have a problem. Those data lines will go to a USB 3.0 hub, so that can indicate that the hub is maybe faulty, or maybe the Southbridge IC is faulty. I suspect that this component here is a TVS, a transient voltage suppression diode. So this diode is a protective component designed to shield electronic circuits from the voltage spikes. These voltage spikes can be caused by lightning strikes, electronic discharge, or a inductive load that is switching. So these components here are filters, and every data line will go to this filter. So this filter will have a direct connection between A and B, but not sideways. So these filters on these USB data lines are used to manage noise, suppress EMI, and ensure signal integrity. These USB data lines will go straight to the Southbridge. So this is a MOSFET that acts like a switch. So this MOSFET is a TPS2021. So this MOSFET gets 5V from the 5V power on rail, and it will pass it through to the USB. So this is 5V USB, and this power rail will go to this pin. And let's say something shorts this line, the 5V USB, then this MOSFET can be turned off because it sees a high current draw. So the purpose of this MOSFET is to protect the system from shorts. So when this 5V USB is shorted, it will be disconnected from the circuit. On the front side we have two USB 3.0 ports. This is located in region 6. So this is the back side of those two USB ports. This is the 5V USB circuit that provides power to the front USB ports, and this is located in region 33. So this is the back side of those two ports. Again, this is the 5V USB power on the first pin here. The data line will go through a TVS diode, from there through this filter, and from here some decoupling capacitors, and these data lines will go to the USB 3.0 hub. Same here, so these data lines will go directly to the USB 3.0 hub. Important here is to know that every data pair, so these two, and these two, the diode measurements should be the same. If one data line of this pair is different, so it reads a different diode measurement, then that could potentially indicate a problem, because the data pairs should be exactly the same. Under the two USB ports, we have two switching MOSFETs. These two MOSFETs will provide power, 5V USB power to the connectors. And under those two MOSFETs, we have a 5V power on buck converter. And this buck converter will generate the 5V that is needed for the different components on the board, but also for the USB ports. These are the two MOSFET. The input will be 5V, and this 5V will come from this buck controller. So this buck controller will convert 12 volt to 5 volt. And this 5 volt will go to these two MOSFET, and the output is then called 5 volt USB. And these two power rails will go to the USB connector. So this chip is the buck controller. It's a TPS53219A. It is designed for converting 12 volt to 5 volt. This is needed by different components, such as the USB ports. This controller is part of a power phase circuit. So this controller regulates the output voltage by controlling the switching of the two MOSFET that is on the other side. You can identify a buck controller usually by its shape. So it's a small multi-pin integrated circuit. One of those connections is a feedback pin, a compensation pin, and some power management pins. So this is the feedback pin. As you can see, the feedback pin is connected to a series of resistors. This is called a voltage divider. And this voltage divider is connected to the output that this buck controller is creating. So the resistor dividers provide feedback to the controller by dividing the output voltage to a manageable level. So it will bring this level down and it will go into this controller. If you can identify the resistor dividers, then you can see that it's connected to the output voltage and to the buck controller on the feedback pin. Pin 6 is the power supply pin. So this will provide 12 volt for this controller to operate. On pin 2, we have the enable pin. So the enable pin should be around 3.3 volts. When this enable pin is low, it will turn off this buck controller. This is the power good pin. It indicates whether the output voltage is within the specific range. When the output is within range, the power good pin is pulled high. Pin 9 is a voltage regulator pin. This pin provides an internal voltage at the linear regulator output. It is used to supply power to the gate drivers and other internal circuits of this buck controller. So pin 5 is the mode selection pin. It has to do with some internal setup for this buck controller. Pin 7 and 8 are ground. So this pin is the high side MOSFET driver pin. It drives the gate of the high side MOSFET, turning it on and off during the switching. And this is the low side MOSFET driver pin. So it drives the low side MOSFET, turning it on or off during switching. This buck controller will eventually generate the 5 volt power on. So if we go to the top side, this is the top side of the PCB board. So the buck controller is located underneath this PCB board. So this is in area 4. So this is where the 5 volt buck converter is located. And this is the bottom side. So this buck controller will drive this high side and low side MOSFET. The buck controller will send the PWM signal to the high side MOSFET to the gate and the low side MOSFET also to the gate, and this will start switching the high and the low side. So on the high side we have the 12 volt power on. So when you press the power button of your console, the 12 volt will be generated from the power supply. This will reach this high side MOSFET. These two MOSFETs will start switching and it will create the 5 volt power on power rail on the output. You can recognize a power phase circuit by these components. So first one, we have the buck controller IC, and the high side MOSFET will be connected to a power source and the low side MOSFET will be connected to ground. So this is ground. So in a power phase circuit, the two MOSFETs are connected together so that the drain of the high side MOSFET will be connected to the source of the low side MOSFET. And this is called a switching node, and the switching node is connected to the inductor, and from the inductor it will go to the output, and on the output we see some capacitors. The high side MOSFET has a different part number than the low side MOSFET. The low side MOSFET will be turned longer than the high side MOSFET, and because of that the current passing through this MOSFET will be higher, and that's why this part number has to endure larger currents. Near the two MOSFET we have the inductor. It's a large coil or a component labeled with an inductance value, so this is the inductance value. You can find this inductor between the MOSFETs and the output capacitors. So the input capacitors filter the input voltage to provide a stable supply to the circuit. The output capacitors will smooth the output voltage by filtering out the switching noise. On the power phase we also have a feedback circuit. So the feedback is connected to the output power rail. It will go to some resistor dividers, and from there it will go to the feedback pin of this buck controller. So this inductor stores energy when the high side MOSFET is turned on and releases this energy when the low side MOSFET is on, and these capacitors will smooth out this output voltage. So this process helps to regulate the output voltage of 5V. On location 9, the USB 3.0 hub controller chip is located. So the data lines of these two USB ports will go to this hub, and from this hub the data lines will go to the Southbridge. This is a USB hub controller chip. So this chip is for expanding the USB connectivity in the PlayStation. So the two USB ports are connected with this chip. This chip supports high-speed data transmission, it handles the power management, and it also communicates with the Southbridge to integrate the USB functionality. So the two USB ports will communicate with this hub, and from this hub it will go to the Southbridge. There are no schematics available for this chip. The power supply for this chip is 3.3V. These are the resistance values. This is a 26 MHz crystal. These data line will go directly to the Southbridge, and the data lines from the USB ports will go into this chip. In region 23, the extension port is located. This is the extension port, and these are the components located near the extension port. This port here is designed for additional functionality, so it's typically used for connecting different peripherals to the console to enhance the gaming experience. And these are the components located near this extension port. The data lines of this extension port will go directly to the Southbridge. All those data lines have a diode reading of 0.34V. So when one of those values is deviated, then you know you have a problem with this port or maybe with the Southbridge. When you turn the console on, 5V has to be present on this pad. I think this is a low drop voltage regulator. So when the console is turned on, 3.5V has to be present on this test pad, and 1.1V should be present on this pad. And I think these two chips are responsible for generating those power rails. The HDMI port is located at region 22, and the HDMI encoder chip is located in region 21. So this is the HDMI connector on the console. When you connect in a breakout board, then you can measure the different pins that are located inside of this HDMI connector. The labels in red are the names of the pins, and the labels in green are the diode measurements, and the label in purple are the resistance values. From the APU, the video signal will go through the encoder chip, and from the encoder chip it will go to this HDMI port, and from here it will go to your display. All the pins that have the TMDS label will send the data or the audio signal from the console. It will send it to your display. So the plus and minus pin of each pair should give the same diode measurement. So in this case 0.48V. When one of those values is different, then you have a problem. This could be in the HDMI port or in the encoder chip or maybe in the APU. So in this case the data line 0 has the same values, so those the minus and the plus lines have the same values. For the data pair 1 minus and plus has the same values. For the 2 plus and the minus line, same values. Here also for the clock lines I have the same values. These two pins are used for the serial communication. So this is the clock line that is used for the timing of the data signals, and the data will be carried onto this line. And both pins have a value of 3.3 volts. On this pin there will be a plus 5 volt power supply present, and this pin is used for a hot plug detect. So when you connect a device onto this HDMI port, the console will detect that there is a screen connected. When the resistance values and the diode measurements are okay, then you can assume that this HDMI port is okay. Again, this is the HDMI port. These are the ground pins. This is an open line, so this is not connected. This is also a ground pin. For each data pair, the data lines will go through a filter. So these filters are used for reducing the electromagnetic interference. So when you have a no display, but the console turns on and the LED is white, then you have to check this HDMI connector. You have to check if all pins are connected. You have to check the Southbridge chip. And also you have to check these filters. These filters should have a continuity between those two pads, but not sideways. The HDMI encoder chip is located in region 21. So this is the encoder chip. This is the HDMI port, and this is the APU. This chip is called an MN864729. There are no datasheet available. This chip is used as a bridge between the GPU and the HDMI output. So this chip will handle the conversion from the display port data that comes from the GPU. It will convert that data to a HDMI signal that will go to the display. When you connect a display on the HDMI port, on the hot detection plug, this signal will go to the encoder chip, and from the encoder chip it will go to the APU. This hot plug detection pin detects when an HDMI device is connected and ready to receive data. Again, if you have no display but you have a white light, then check this HDMI connector, check the Southbridge chip, and also check this HDMI encoder chip. Also check if the filters are okay. On this pad, when you turn the console on, the 2.5 volt should be present, and also the 3.3 volt should be present. On this capacitor there should be 2.5 volt, and on this pad there should be 3.3 volts. Also on this pad there should be 3.3 volts. Also check if this diode is not shorted, because if it is shorted it can cause a blue light of that. The HDMI signals comes from the APU. It will go to this encoder chip. This encoder chip will convert the display port data into an HDMI signal, and it will send it to the HDMI port. This chip will also send the clock signals to the HDMI port. This is the backside of the HDMI circuit. This is located in region 50. So on the backside these components are located. When you have no display, check the diodes in this region, and also check if this fuse isn't broken. On this pad there should be 3.3 standby voltage present, and also on this pad and this pad. And in the green are the diode measurements. So if you find some deviating value here, then this could indicate a problem with this component or somewhere else. Again, we have the fuse here, so these are the resistance values. When the console is turned on, 2.5 volt should be present at this pad, 3.3 volt present here, and 2 volts present on this pad, and on this pad there should be 3.3 volt. You should measure 12 volt on this pin and 5 volt on this pin, and 3.3 volt should be present on this pin. This chip here is a power management chip, and this chip will generate different standby voltages, and these voltages will be used by the Southbridge chip. This chip is located in area 43. This power management IC is an RT5069A. This is a DC to DC synchronous buck converter. So this power management chip regulates different voltage rails that is required by different components like the Southbridge within the PlayStation 4. On this pad here you can find a 3.3 volt, also at this pin, this pin, this pin and this pin. On this pad you can find the 1.8 volt. On these two pads the 2 volts will be present, At this pad you can find the 5 volt. When you turn the console on, you can find 1.5 volt at this pad. Most of these voltages are standby voltages. In region 45, we can find different capacitors that are located beneath the APU, so on the bottom side of this PCB board, and on the other side the APU chip is located. In this region you can measure the voltage of 0.9 volts and also 1 volt that will be present on those capacitors. These are the capacitors that are located on the back of the APU. These capacitors are needed for the power delivery, signal filtering and stability. So these capacitors are placed near the power pins of the APU and it serves to filter out high frequency noise and fluctuations from the power supply. So when you measure the impedance of these capacitors, these are really low, so they should be around the 1 or the 2.5 ohms. So the other end will be connected to ground and the other end will be a low resistance. On this capacitor you can measure the CPU voltage of 0.93 volts. And on this capacitor you can measure the GPU voltage of 1 volt. By measuring the impedance of these capacitors you can check the health of the APU. So one side of the capacitor is connected to ground, and if the other side is also going to ground, so it has 0 ohms, then you know there is a short. This short can be in a capacitor or the APU itself. In region 2 there is a power phase located, so this power phase will also go to the GPU or APU. This one is a different power phase because these 5 power phases are parallel connected, so this voltage will eventually go to the APU. And this has a separate power rail, so I think this power phase will be used by the CPU part of this GPU. On the bottom side you can find 2 capacitors that are located at the output of this power phase. This power phase will generate a voltage, so the output will go to the bottom side. So the output voltage can be found in region 46, and I think this is one power phase that will be used for the CPU part of this GPU. So these are the 2 capacitors, this is the output. And on the output we can find the CPU voltage of 1.1 volt. The resistance value of this output is 1.9 ohm, so it is very low resistance. In region 48 we can find the voltages of 0.95 volt and the 1.8 volt. I suspect that these 2 chips are the low drop voltage regulators, and these 2 regulators will create 0.9 volt and also the 1.8 volt. So this is the output. On the 4th pin there is a 1.9 standby voltage present, also on the 4th pin of this chip. On these 2 pads 3.3 voltage is created. These voltages are being created when you turn on the console. Also the 5 volt is present here. And the 5 volt that is present on this pad is a standby voltage of 5 volt. These LDO regulators are designed to operate with a very small dropout voltage. It's typically in a range of a few hundred millivolts to a volt. So the difference between the output and the input is very small. So the input is 1.9 volt and the output is 1.8 volt or 0.95. These 2 output voltages are being used by the APU. The RAM ICs can be found in region 49. So we have 8 GDDR5 memory modules, and these are located here. This is a GDDR5 module. So this memory is used for storing textures, frame buffers and other graphical data that is necessary for rendering high resolution graphics. Those capacitors are needed for stabilizing the voltage power supplies for these RAM modules. So the layout of this RAM module is the same for the other modules. Most of them have the same capacitors and resistors surrounding the RAM module. So at these resistors, if you measure it in resistance mode, is around the 120 ohms, 1.6 kilo ohms and the 2.5 kilo ohm. If you compare these values with the other RAM module, it should give you the same results. When you measure the impedance of these capacitors, you can check the health of this RAM module. So one side will be connected to ground and the other one should read a value around the 59 ohms. The Wi-Fi and Bluetooth circuit is located near region 57. So this is the Wi-Fi and Bluetooth chip. When you have problems syncing your game controller to the console, it can be the cause of a bad or faulty Bluetooth and Wi-Fi module. So if this module is faulty, it gives sync errors. These test pads here are the data lines, so the input and output goes from the Southbridge chip to this Wi-Fi module. In green are the diode measurements, and in the red are the standby voltages. So on these pads you can find the 1.8 volt standby voltage. The following components are married to the board. So first one is the APU, so you cannot change the APU with another APU. Next we have the first and the second DDR memory that is used for the Southbridge. So this is the first DDR memory. This is the second one. And this memory is used for the Southbridge. If one of those chips is failing, then you cannot repair the PlayStation 4. Also, if the Syscon IC, so in region 36, if this chip is failed, you cannot repair the PlayStation 4. Also, when the Blu-ray controller is failing, then you cannot repair the PlayStation 4. And that is because all these chips are married together. So if one of those chips is failing, you cannot replace it with a donor chip. So this is the first and the second memory. This is used by the Southbridge. Then we have the Syscon IC. This is the APU. So this is the NOR IC. In this chip the firmware is stored. And then we have the Blu-ray controller. So it can be a Mediatek IC or a Renesas IC. So if one of those chips is faulty, you cannot replace it by a donor chip. This is the Southbridge, and underneath there is a DDR memory in region 65. The second DDR module is located on the bottom side of the PCB board. And in region 44, this is the RTC clock. So this is the crystal oscillator that generates the signal of 32.768 kHz. So in this region, the power button ribbon cable is connected into this connector. Most of the time the Southbridge is faulty on a PlayStation 4, and this can cause a no power condition. So you have to check the capacitors underneath the Southbridge on the bottom side of the PCB. Check this region for shorts. Also, the power that is needed for the Southbridge and some other components near the board is generated by this power management chip. And this power management chip will generate different voltages. In the previous slide you could see which voltages needs to be present for the Southbridge to work properly. So if these voltages are not okay, the Southbridge will not operate, and then when you press the power button nothing will happen. So always check if the 3.3 standby voltage is present at this power button connector. So the ribbon cable from the console where the power button is located will come into this connector. This voltage is needed to send a pulse back to the Southbridge to indicate that the power button is pressed. So if this voltage is not present, then you have to troubleshoot why this voltage is missing. Next, check the power supply if the standby voltage of 5 volt is being generated. And when you press the power button, check if the 12 volt power on is generated. Also check the board for burnt or damaged or missing components. You can also test if you put a disk in the Blu-ray drive to see if the console powers up, because that will initiate a power on request. You can also press the eject button to see if the console makes a sound. If yes, then you know the standby power is present. If you press the power button and the console only beeps and you don't see any LED indication, this could indicate that there is a missing 3.3 volt problem. So check if the 3.3 volt is present. This is a crystal oscillator. This oscillator will create a frequency of 32.768 kHz. And this oscillator should be working all the time. Always check if the RTC battery is higher than 3.0 volts. When this frequency is missing and you press the power button, nothing will happen. So you have a no power condition. Always check if this frequency is present. Check the RTC battery if the voltage is 3.0 volts. These are the diode measurements for the crystal oscillator. So these are the two DDR memories that are working with the Southbridge. And on this capacitor you can measure the RAM voltage of 1.5 volt. And as you can see here, the resistance is 1.3 kilo ohm on this power rail. And for this VTT power rail, the resistance is about 5 kilo ohms. The same is for the other RAM module. Here you can find the VTT voltage of 0.7 volts. And on this capacitor you can measure the 1.5 RAM voltage. For the video RAM it's the same here. So you can measure the 1.5 RAM voltage at this capacitor. And at this resistor you can measure 1 volt. And this layout is the same for all the different RAM modules. So this is a different one. And you can measure here the 1.5 RAM voltage and the 1 volt at this resistor. Near the Southbridge you can find the NOR BIOS IC. So the IC is located here in region 47. This chip here is a NOR flash memory. NOR flash memory itself is a versatile technology used in the PlayStation for storing the BIOS firmware, but also some extended firmware. So this is a more advanced chip than the BIOS. This chip communicates with the Southbridge. This is the pin out of this NOR IC. The first pin is chip select. Then we have serial output. Serial input is on pin 5. Then we have the clock signal that will go to pin 6. This is the power supply. This is write protection and this is ground. First, when you turn on the console, you have to check if the clock signal is present at pin 6. So here you can see the clock signals. It's something like this. You can check this with an oscilloscope. Also, you can check 1, 2 and pin 5 for communication. So when you probe this pin, you can see some communication going through this line. So when the data is coming into this flash memory, you see it on oscilloscope, then you know the Southbridge tries to communicate with this NOR IC. On the output side, if there is no data coming out, so we see data coming in but there's no data coming out, then most probably this NOR IC is bad or faulty, or the firmware is corrupted. So then you know that the problem lies with this chip. You can test this NOR IC in standby mode or in the power on mode. You can check those communication pins to see if there is data communication between the IC and the Southbridge. So this chip needs a standby voltage of 3.3 volts, that is on the 8th pin. This chip here is a multi-phase buck controller. This is IR35218. This chip will send the PWM signals to all the different power stages. So we have 6 power phases here and 2 phases here. And this chip will coordinate the PWM signals to these power driver ICs. And these power stages will generate the V-core for this APU, for the memory and the CPU. So this is the multi-phase control chip. This is the IR35218. There are no datasheet available. I did find an alternative datasheet. You can see that in the next slide. But for now, this is the buck controller. This buck controller will drive 5 power stages for the GPU, 2 power stages for the CPU and 1 power stage for the random access memory. These resistors here are the current sense resistors. In green are the diode measurements. On this pad here you can measure the power supply of 3.3 volt. This will go to the VCC pin. All the pins here are the PWM signals. So these signals will go to the phase driver IC. On this pad here you can measure the 3.3 volt and also on this pad, and these pads are used for the serial communication that will go to this chip. This 3.3 volt has to be present to enable this chip, and if it's enabled, this chip will start working. On this pad you can measure 3.3 volts, on these 2 pads 1.7 volts, also on this one. On this pad you can find the power good signal, that should be 3.3 volt. So if you find 3.3 volts here, then you know this buck controller is working correctly. Then we have a power OK signal of 1.8 volt that can be found here. On this pad here it will go to the voltage in sense pin. And on this pad here you can find the 3.3 volts. So in a good working buck controller you should see these diode measurements and these voltages. So this is the alternative datasheet of the buck controller. On the upper side you can find the current sense resistors. So the 3.3 volt power supply will be connected to this VCC pin. Then we have the serial communication pins here. These are the PWM signals that will go to the power phase driver ICs. The enable pin, the voltage in sense, the power OK pin, power good signal. So as you can see, this datasheet is almost the same as this implementation here. In region 2 and 3 you can find the power stages, and these chips here are the power stage driver ICs. We have 5 that will go to the GPU and 1 will go to the CPU part of this GPU. So here you can find the GPU power stage driver ICs. This is the main buck controller, so this will send the PWM signal to the power stage driver ICs. So you can find it here on these pins. The 12 volt will go into this part, and on the other side the GPU voltage of 1.1 is generated. This is the datasheet of this power driver IC. So 12 volt will go into these 6 pins. So the PWM signal from the buck controller will go to pin 40 and the output will be generated on these pins. This configuration is for every IC. And every PWM signal of this power stage driver IC will come from a different pin from the buck controller. If there is a short on the output, you have to disconnect this coil to check which power phase is faulty, because they are all connected in parallel, the output. Why do we need 6 stages to generate the GPU voltage of 1.1 volts? Because more phases help in distributing the load more evenly. Also, by having multiple phases, the ripple effect, so the voltage fluctuations, is reduced. So it leads to more consistent power supply. The RAM voltage or memory voltage of 1.5 volt is being generated by this power stage. And this power stage is also controlled by this buck controller. So this phase is located in region 19. The power phase driver IC is located at the bottom side, so in region 51. And this power driver IC gets its PWM signal from the buck controller. So the PWM signal from the buck controller goes to this power stage driver IC, and this will generate the 1.5 volt that's needed for the random access memory. So this was the top side of the power phase, this was the bottom side. One of these MOSFET is the high side MOSFET and the low side MOSFET. The power supply source for the high side MOSFET comes from the 5 volt standby voltage or the power on voltage of 12 volt. So that will be entering this MOSFET. So this is the low side MOSFET, and one side will be connected to ground and the other one to the common source. These 2 pins are the gates of these MOSFETs, and the PWM signal that will go to the high side and the low side MOSFET comes from this driver IC. The high side PWM signal comes from this pad, and the PWM signal for the low side comes from this pad. At this pin you can find 5 volts, and also I think that this pad here is a feedback signal. That is because I see a voltage divider, and the voltage divider is always connected to a inductor. So from the output it will go to the voltage divider and then into the power phase driver IC. So that is how you can recognize a feedback circuit. When these MOSFETs are switching, it will generate a RAM voltage of 1.5 volt that is needed for the random access memory, and the impedance of these RAMs are 56 ohms. Also, the power supply input to this high side MOSFET comes from the 5 volt standby, and when you turn on your console it will come from the 12 volt. Here you can find one power phase that will generate a voltage for the CPU. Also, this power phase is driven by this buck controller. It will send the PWM signal to the power phase driver IC that's located on the back side. The power phase driver IC is located on the bottom side of the PCB board. It's located in region 53. This is the top side, so this is the high side MOSFET and the low side MOSFET. This is the output, this is the inductor. The PWM signal from the buck controller will go to the power phase driver IC into this pin. So this IC will drive the high side MOSFET and the low side MOSFET. So this pad here will go to the gate of the high side MOSFET, and this pad here will go to the gate for the low side MOSFET. This MOSFET will start switching. It will generate a CPU voltage of 0.96 volt, and the impedance of this power rail is 19 ohms. At this capacitor you can find 5 volts. Here you can find a 12 volt inductor. So from here the 12 volt will go into the different power phases. When there is a short on the 12 volt line, you want to isolate this circuit. And you can do this by removing this coil or the inductor. So this is the main coil filter. 12 volt will go into this coil, and from here it will go to the different power phases. So when you have a 12 volt short, you want to remove this coil to see if the problem is beneath the power phases or in the other part of the circuit. And by removing this coil, you can isolate those two circuits. So in this region you can find the Blu-ray motor controller, also known as a Blu-ray motor driver IC. It's located in region 37. This is the motor driver IC, it's the BD7764. This driver chip is used as a motor controlling device for the Blu-ray drive. In the PlayStation 4, the motor driver is used to control the spindle motor. It ensures that the Blu-ray disc spins at the correct speed for reading the data. So it will move the optical pickup unit, where the laser is located, to access the different parts of the Blu-ray disc. There are no datasheets available for this chip, so I cannot tell you much about it. In green are the diode measurements, and if you see a deviating value, then maybe this chip is faulty. This is the Blu-ray controller chip. This is located in region 13. So this chip can be a Renesas chip or a Mediatek chip. And both of those chips are used for controlling the entire operation of the Blu-ray drive. This chip is married to the board, so if this chip fails, you cannot use it anymore. So this controller chip will drive the entire operation of the Blu-ray drive. It will manage the spindle and loading, ejection and sled motors. It will also adjust and focus the laser. It will do the error correction and also the encoding and decoding of data. It will also communicate with the host system and execute some specific commands from the APU back to the Blu-ray drive. This chip also monitors and reports errors back. So in short, this chip will control the Blu-ray drive to read and write data accurately. It also manages the disk loading and ejection and maintain the interaction with the host system, so in this case the APU. This is the Blu-ray drive. It has 3 ribbon cables. So the first goes to this connector, and from here it will go to the Southbridge. I do not know exactly what this does, but I suspect these are signals that comes from switches within the Blu-ray drive, and this signal will go to the Southbridge. Then we have the bigger cable. This will go to this connector, and from here it will go to the Mediatek or the Renesas IC. The data will go to this rubber cable. From here it will be processed by the Mediatek chip, and from there it will be sent to the Southbridge. Also, for controlling the motor, it will send signals to the motor driver IC. This connector here will provide the voltages needed for the motors. It will go to the ribbon cable and it will drive all the motors that are located inside of this Blu-ray drive. So this part will drive all the motors. So this part is responsible for reading and writing the data. When you insert a drive into this Blu-ray drive, it will send a signal to this connector. From here it will go to the Southbridge, and the Southbridge will turn on the console. Because we don't have any schematics or data sheets, when you want to troubleshoot it, you can compare it with these diode measurements and these voltages. This chip here is a Syscon chip. It's located in region 36. You can recognize a Syscon chip by the marking like A05 or Col2. This chip is also married to the console, and this processor is responsible for different low-level management tasks. First, it is responsible for the power management. Also, it is responsible for the temperature monitoring. It is also responsible for the system reset and also communicating with the different components that are located on the main board. The most important part is the security part. The Syscon chip plays a role in the security architecture of the PlayStation 4. It helps manage the secure boot processes and verifies the system integrity. This is the datasheet of an alternative chip. This is just a microcontroller that you can program to use with different input and outputs. It also uses serial communication, PWM signals, etc. The functionality of the chip depends on how it's programmed. After some reverse engineering, these are the most important parts that I could analyze. There are a lot of analog to digital converters configured. We have some interrupt ports, timers. We also have multiple serial communications ports. So here's one, here's one, here's one, and here's one. We have different interrupt ports. We have an output buzzer, a programmable clock, some RTC functionality. This is the VDD, so it requires 3.3 standby voltage. In region 14 you can find the SBV IC, and this chip will generate the standby voltage of 1.9 volts. This is the SBV IC. This chip needs a power supply of 3.3 volts. This chip needs an enable voltage of 1.4 volts. And this chip will start generating standby voltage of 1.9 volts. And I think this voltage is needed for the Southbridge. This chip is also known as a TLV62090. It's a step down converter, so it will step down the 3.3 volts back to 1.9 volt. This is Pinout and this is a example circuit. The power supply input is at pin 11 and 12. Pin 13 is the enable pin. The switching pin where the output voltage is generated is at pin 1 and 2. When this chip is operating okay, it will send a power good signal on pin 4. Pin 5 is the feedback pin, and the feedback pin is connected through a resistor divider, and that resistor divider is connected to the output. On these pads you can find the 5 volt standby voltage. So this is the feedback pin, this is the power good pin. This pin does some internal logic. The output is on pin 1 and 2. Pin 16 is the output voltage sense pin, so this pin is connected directly to the output. In region 20 we can find a enable and disabling circuit of 3 volts. And I think this is an enable and disable circuit because of those 3 transistors. If you see transistors, it's most likely some kind of enabling disabling system. What it exactly does, I don't know. Here you can see the 3 transistors. When you turn on your console, there should be 3.3 volt present at the top side. I think this pin are the bases of this transistor, and the resistance of those bases should be around 9 kilo ohms. Each transistor can disable the 3.3 volt, so it can short the 3.3 volt to ground, and if it is grounded it will not boot up the system. In region 10 you can find the buzzer circuit, and when you hear a beep from your console it comes from this buzzer. This is the buzzer, and when you turn your console on you can find 3.3 volt at this pad, and at this capacitor you can find 1.2 volt. In region 15 this is the bottom side of the Southbridge chip, and on the bottom side you can find the 1.8 volt, 3.3 volt and 1.1 volt. So if you measure the capacitors near this Southbridge you can find these voltages. So this is Southbridge from the bottom side. When you probe these capacitors with a multimeter you can find 1.8 volt, 3.3 volt and the 1.1 volt. The Southbridge fails a lot, so check for short near these capacitors. If you find a short, check if the capacitor is faulty or the Southbridge chip. Most of the resistance value from these capacitors is above 600 ohms. So one side will be ground, that is 0 ohm. So the other one should be above 600 ohms. So in region 29 you will connect the power supply cable to this connector. So this is the 5 volt standby connector. And on pin 1 there should be a standby voltage of 5 volt. Second pin is ground. The third pin is a power good pin. So if you power on the console there will be a 3.3 power good signal on this pin. Pin 4 is the enable signal. So if you want to check in standby mode if your console is reacting correctly, what you can do is connect a 5 volt at pin 1 from your power supply, second pin to ground, and pin 4 you have to connect it back to pin 1 so that pin 4 gets 5 volt. When you do this, the standby boot sequence will be started, and in a normal boot what you would see on your lab power supply is that it will start from 23 milliamps, it will jump to 125 milliamps, and then it has to settle back at around 30 milliamps. If you see this boot sequence, then you can conclude that your console is reacting correctly and it should work. When you turn your console on, the power supply will deliver 12 volt, and the 12 volt will go to this connector. So in region 28, the 12 volt connector is located here. So the top side is the ground connection, and on the bottom pin, the power supply will deliver 12 volts. In region 24 you can find the optical audio output. So this is the optical output connector, and this is the surrounding circuit, and at these two pins you should find the standby voltage of 3.3 volt. On this pin you should find 1.9 volt, and when you turn on the console you should find 3.3 volt at this pad. In this region the power supply of 5 volt is being created for the SATA drive. So this is in region 17. So this is a SATA connector. This is the voltage regulator that will give 5 volt to the SATA connector. So when you turn your console on this pad you should find 3.3 volt, and then you should find 5 volt at this pad. On the second pin you should find also 5 volt. And on this pad you should find the 5 volt, so this will go to the SATA connector. In region 60 there is some power circuit. So this is the power circuit. I do not know exactly what it does. I think this is a diode. When you turn the console on you should find 3.3 volt on this pad, and 12 volts on this pad, and 7 volts on this pad, and on this pin you should find 12 volt. And on the other side of the diode you should also find 12 volt. When you turn off your console, so you're in standby mode, the on voltage should not be there. So on this pad, instead of 7 volts you should see the standby voltage of 4.5 volt, also here and at the other end of this diode. So on the bottom side of the PCB board near the RAM modules you have some test points, some data lines. That is in region 58. These are the test points, and the purple values are the resistance values. So all the test points should be around the 37 kilo ohms. What the purpose of these test pads are, I don't know. Near the power phases we also have some circuitry. This is located in region 59. So this is the circuit near the power phase. When you turn your console on, it should get 3.3 volt at this pad, and on this pin there should be 5 volt present, and at this pin there should be 3.3 volt present. So near the buzzer we have some circuitry that's located in region 10. When you turn your console on you should find 5 volt at this pin, and at this pad you should find 3.3 volts, 2.2 at this pin. I think this circuitry is used to drive this buzzer. This is the fan connector. The fan needs 12 volt, and this is in region 31. So this is the connector. On the first pin there should be 12 volt present when you turn the console on, and the resistance is higher than 400 ohms. The second pin is ground, and the third pin is where the PWM signal comes from the APU. So the APU will send a PWM signal to pin 3, and this will drive the fan. So the fan internal circuitry will interpret the PWM signal and adjust the speed of the fan motor. To reflow this APU you need a rework station, and you have to set a specific temperature profile. So this is my personal temperature profile for removing or reflowing a APU. So So I start my bottom heater at 185 degrees. It will dwell for 480 seconds. After that, the top heater will turn on. And the top heater will ramp the top temperature up to 190 degrees. And it will do that in 1 degrees per second. It will wait around 76 seconds. And after that, it will ramp up to 200 degrees. It will wait 46 seconds. And then it will ramp up to 210 degrees. And then it will wait 32 seconds. And in this region, I will reflow the APU. If the APU is not reflowed, you can ramp up to 228 degrees. In this region is the danger zone, because in this zone you can damage your APU because the temperatures are very high for a long time. When you are in this reflow region, it's best to reflow your APU. This phase is called the preheat phase. In the preheating phase, the bottom heater will rise the temperature of the PCB board up to 185 degrees. Then we have the soak phase. In this phase, the temperature is increased to a level where the solder begins to melt and flow, but the BGA or the APU is not yet reflowed. After the soaking phase, we will get into the reflow phase. During the reflow phase, the solder transitions from a solid to a liquid state, creating solder joints between the APU and the PCB pad. Once the reflow phase is complete, the board is gradually cooled down. So this was my analysis about the PlayStation 4 mainboard, especially for the model NVB003. But as you know, there are a lot of different types of boards and models and series. In the next slide, I will discuss those different boards in a more generic way. So this is the main board of the type SAA or SAB. This is the layout of it, and as you can see, the circuitry is almost the same. The components are almost the same, only the layout and maybe some refactoring or optimization of the circuit is present. But the big picture here is that you can identify the power phases, the APU, GPU, the RAM modules, the Southbridge, the Bluetooth IC, the power connectors, the SATA drive, buck converters, buzzer circuit. As long as you can identify those components, you can troubleshoot any board. So this is the Syscon IC. Again, APU, the RAM modules, all the same. This is the RTC battery. It's the 12-volt power supply. So it will go to this inductor, and from there it will go to the power phases. This is the 12-volt power supply. The standby 5-volt connector from the power supply. This is the Blu-ray drive connector, the Blu-ray drive data connector. This is the Wi-Fi Bluetooth chip. This is some DDR memory. This is the SSD or the HDD controller. And this is the hard disk connector. This is the Southbridge, DDR memory, Syscon chip. I do not know what this is. This is the NOR or the BIOS chip. This is the crystal oscillator, the Ethernet controller. This voltage regulator will generate some standby voltages. This is a 25 MHz crystal. This is a buck converter that will deliver the power to the RAM. So this is the multi-phase buck controller. It will send the PWM signals to each of these power phases that will deliver the power to the GPU or the APU. This is the USB hub controller. So this USB connector 1 and 2 will go to this hub. From here it will go to the Southbridge. Here are the LEDs located. On this main board there is no connector for the power button, but there is a touch power button. So when you touch this button, it will turn the console on. So this is the back side of the Southbridge. If there is a short here, most probably your Southbridge is faulty. This is the HDMI connector, and behind this shielded plate there is the HDMI encoder IC. In the next slide we will go to a different type of mainboard. And this is the mainboard of type SAC. This is a layout of type SAA or SAB. And the layout of an SAC board is different. But now we can identify the components. So this is the APU. These are the power phases. So somewhere there should be a buck control that will send the PWM signal to the power phase driver ICs. So these are the power phase driver ICs. and underneath the bottom side of this PCB board. That will generate a output voltage, and from there it will go to the APU, CPU or GPU part. We have some hard disk connector here, some power supplies, some voltage regulators, Southbridge, Bluetooth Wi-Fi chip, the buzzer, HDMI ports, optical port, RTC battery, fan connector. So as you can see here, we can now identify all those different components. This is a different mainboard. This is of type SAE or the SAF. The layout is different, but now we can identify the components. So these are the two USB ports. This is the RTC battery. Some kind of voltage regulation going on here. We have some power phases here. Also some power phases here. And a power phase here. I think this is a Southbridge. Some BIOS chip, I think. Some Blu-ray drive control circuit, some enabling circuit here. As long as you can identify all those components, then you can troubleshoot it by measuring the enable signals, the power supply signals. So these are all the different types of boards that you can find on the PlayStation 4. As long as you know how to find shorts and which components are available on your mainboard, then you can try to troubleshoot it. This was the final slide of the PlayStation 4 troubleshooting and analysis video. I hope this video helped you to get more in-depth knowledge about your PlayStation 4. Because there are so many different types of boards available, it is for me impossible to make specific videos about these boards. That is why it is better to identify these components on those boards and use this information to troubleshoot and analyze it. If you like this video and you want to see more, then don't forget to give a thumbs up and hit that subscribe button for more in-depth circuit analysis. Thank you for watching. Until next time, bye bye.